Next talk is by Stavros Garoufalidis from Jul2Wed, and he will speak about introduction to the Slope Conjecture.
Thank you very much for the kind invitation. I am a little embarrassed to be an organizer. There are several organizers of this conference, but I really want to thank especially Rinat, because I think if it was not for Rinat, this conference would not have happened. So I want to talk about something called the Slope Conjecture. So a few years earlier, about maybe 3 years or so, or 4 years, there was another conference here, also organized by Rinat, in VideoSeries, and I guess somewhere there. And at that time, I had talked about beyond the slope conjecture, but then I realized several years later that you shouldn't just rush to talk about the latest, but you should give some time, to catch up and realize what this is about. So I want to give a very gentle introduction to the slope conjecture, and please, if you don't understand something, just stop me. Okay, so the slope conjecture actually relates a well-known quantum invariant and that is the degree of the Jones polynomial of a knot and its parallels. So that's a quantum invariant to a classical invariant, and a classical invariant, classical topology invariant, namely slopes of incompressible surfaces. In the knot complement. K is a knot. Okay, so and relates, it's not a sort of abstract relation, it's a very precise relation, and I will just formulate, I'll just tell you in symbols what slope conjecture says, and then I will define the left-hand side and the right-hand side. So it is a conjecture that involves that it has two sides, each side can be computed, and the conjecture says that they're sort of related. So if K is a knot, the slope conjecture says that 4 times Js of K is a subset of Bs. Okay, that's what it says. Now I have to explain to you. So what is Js? It's obviously a set, and Bs is also a set.
4 has a 2 for me.
And 4, so it had better be a set of real numbers or complex numbers, actually. Okay, so I will start with the right-hand side, which is supposed to be also classical. And by classical, I mean classical algebraic topology of the 60s. And by that I mean basically Haken, when people were interested in the 4-color theorem. And that topology has resurfaced in the 80s by the work of Bill Thurston on hyperbolic geometry of 3 manifolds. And much more recently, this was settled by basically the work of Ian Agol, who finished the remaining part of geometrization's ideas of Thurston, namely existence of incompressible surfaces in hyperbolic manifolds, up to finite covers. Okay, but we don't need to be very fancy here, so all right, we have what we have. We have a knot K and its complement M, which is a 3-manifold with torus boundary. And since it is a knot complement, the boundary is not just an abstract torus, but in fact it is a torus where we have a preferred basis for the homology, and not even basis for the homology, a preferred system of two curves, one for meridian and one for longitude. The meridian goes once around the knot, and the longitude kind of follows the knot. So, and that is the boundary of that knot complement. So, what is a surface? Sigma is a surface. So, surfaces for us will be compact surfaces, but they will also have, they are allowed to have boundary components, several boundary components. So, a surface of genus 2, oriented surfaces, although that's not so important. So they have some genus and they have some number of boundary components. And these surfaces, to the very least, are going to be embedded in the manifold. But if you have a surface with boundary, where will the boundary of the surface go? To the boundary of the manifold. So these are proper embeddings. So I'm only going to be talking about embeddings of surfaces where the boundary of the surface goes to the boundary of the manifold. Now, the boundary of the manifold, we decided that was a torus, a standard sort of torus. And the boundary of the surface, well, I guess we all know that it is a circle, or rather, not quite a circle, but a finite union of circles, right? Here, 3 circles. And each circle will become a circle on a standard torus, so I need, if I have 3 circles here, these 3 circles will become 3 simple closed curves in the standard torus. So let me try again my standard torus, and here is curve number 1, and here is curve number 2, and here is curve number 3. Could these 3 curves be the boundary of an embedded surface in the manifold? Actually, that is a question for the audience.
No.
No. Obviously not, because whatever a surface is, these 3 circles, abstractly, they are disjoint. Therefore, their images, even if they happen to kind of, well, their images have to be disjoint, and even if you consider curves up to isotopy, there is no way to make these 2 curves disjoint from each other. So that picture is just not possible. So if that's not possible, let's remove it and make it
to be disjoint.
Because the boundary components of a surface are always disjoint.
Well, but when you map something, then
Embedded.
Oh, it's embedding even for the closed.
Yes,
okay.
Yes. Oh, I should have.
Okay.
I am embedded.
So you're requiring.
I did say properly embedded. So okay. So basically, then the only thing that can happen is that okay, you have these 3 boundary components are 3 simple closed curves, which are actually co-bound little annuli, and all that means is you take one simple closed curve and you just take 3 parallel copies of the curve, and that's basically all you have. Now, since our torus has a canonical kind of basis of curves for a meridian and longitude, every simply closed curve, so every simply closed curve gamma on the torus is M is P times meridian and Q times longitude, where P and Q are co-prime integers, and therefore it has a slope, and the slope is, I guess, it's P over Q. Okay, and if it's going to be P over Q, it's really going to be a rational number with perhaps infinity if you allow for 1 over 0. Okay, so every time I have an embedded surface in a manifold, in a knot complement, the embedded surface will have several boundary components, and these boundary components, any one of them is going to have that slope. The same slope, because they're really parallel components here, so, and we're going to say that this is the slope of a surface. Okay, the slope of a surface, of an embedded surface, is just the slope of any one of its boundary components.
Why three circles?
Yeah, because 1, 2, 3. I mean, I have 3 boundary components, right?
It's not always 3.
It's not always 3, and it's not always 2, but
But today it's 3.
just, I mean, 3 is a generic number. I wanted something which is more than 1, because if it's 1, you will think that every surface has 1 boundary component, and that's just not true.
But
No,
they could
he
be
thought they
contractible.
Huh?
They could be contractible.
Yes, I mean, that's right. That's an excellent point. So there is some cheating happening. So, and the cheating is the following. I said every simple closed curve can really be written as P times a meridian and Q times longitude, where they are co-prime. Cheating occurs when both P and Q are equal to 0. How can I draw such a curve? Well, you just draw a curve on the torus, which actually bounds a disk, right? You draw a curve on the torus which is null homotopic, and it bounds a disk on the torus, and then of course you get into the 0 over 0 case, and that's cheating. Okay, so we need to exclude cheating. No cheating. No cheating means that the surfaces are going to be embedded, and they're going to be incompressible. Incompressible actually means that pi1 of a surface injects to pi1 of the manifold. So not only the surface embeds, but on the fundamental group it injects. Actually, you need something called boundary incompressible, because, to be honest, that was a trivial loop in the fundamental group of the surface, which bounds a disk. So it's incompressible and boundary incompressible. But anyway, that's kind of, don't worry too much about it. It's clear that this is cheating and we don't allow it, so we're only going to look at surfaces which are embedded. So let's look at surfaces.
It seems that what you actually need is that pi1 of d sigma injects into pi1 of dm. I mean, the circles embed into
That too.
Yeah.
Mm-hmm. That's called, yeah.
So
That's why I said
yeah, no,
incompressible,
but you
comma, boundary incompressible.
oh, both.
Yeah.
Okay.
That's right. As was sort of done in the 60s. So now I'm going to look at these surfaces which are embedded and incompressible, and I'm going to look at their slopes, and okay, I'm going to look at the slopes, and the collection of these slopes is really Bs of k. If we're talking about, it would be Bs of M, where M is the 3 manifold in question, and it's Bs of k, right? Bs. Not Bohr-Sommerfeld, but just Bs. Any question about this?
Is it finite?
Yeah, that's right. So here are that's right. So now we can actually talk about some good stuff. So the first of all, there are infinitely many. So this set is infinite. There are infinitely many incompressible surfaces on a non-trivial knot complement. Okay, that set is infinite, and that's kind of bad news. But the good news is that Thatcher proved in early 80s that Bs is finite. always finite. Not just for a knot complement, but for any three-manifold with torus boundary, okay? Or actually, for any closed three-manifold, I mean, for any three-manifold whose boundary is a union of tori. So this kind of thing is not just one torus. So this is a finite set, although there are infinitely many incompressible sort of surfaces. So, okay, so at least we know that this is a finite subset of rational numbers.
You mean S of gamma, right?
I meant
It's the set of rational numbers. So it's S of. No,
In the definition of BS, it's S of sigma.
oh
of
yeah,
gamma of
S.
S of sigma.
Yes, S of sigma. I got confused with my own Greek letters. Okay. So I need to give you an example because examples are great, I think. So let's compute BS of the -237 pretzel knot that actually already appeared in Don't Stop, but it's always a good idea to draw it. So -2 here, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. That is the -237 pretzel. Okay, so let's compute this finite set. And this finite set is, in fact, 0, 16, 37 over 2, and 20. So there is actually, yes, exactly. So there is an algorithm of Hatcher and Ortel for computing this finite set for certain classes of knots, and those classes of knots is a merge of so-called two-bridge knots and pretzel knots, and they merge together to something called the family of Montesinos knots. And for Montesinos knots, there is an algorithm for computing this finite set. Just because there is an algorithm doesn't mean that it's very easy. And in fact, the original paper of Hatcher and Ortel had 3 versions of output, the printed one and 2 corrections, and then was further corrected by Nathan Dunfield, and who published the final correction. And I think by now the algorithm is kind of straightened out. And yeah, that is the answer. Okay, but I'm not going to say more about this. So now I can tell you something about the left-hand side. The left-hand side, which is this JS of K. So maybe I can do that here. All right. So luckily, I'm sorry I spent a lot of time introducing classical topology, but on the quantum side we're in a much better shape because of previous speakers, really. So K is a knot, and then JK of M is the Jones polynomial colored by the n-dimensional representation, as Tan, for instance, told us a lot about yesterday and really defined it. You may remember a q to the quarter fractional power that shows the power of the people who know quantum groups. I'm only using actually 0 frame in here. So, and if you have 0 frame, then, and you normalize it appropriately, like 1 for the unknown, but that doesn't really matter, then you're going to get integer powers of q. But it is a Laurent polynomial. And out of this, I'm only going to be interested at the degree. So this is the degree with respect to q of this polynomial, okay? So if the polynomial was, I don't know, q to the -3 and 2q square and q to the 5, the degree, I mean, you know, you just look at 5, right? And that means that you're really thinking that this power is much bigger than any other. So this is really the Q equals infinity expansion of the Jones polynomial. You could have used the Q equals 0 expansion, in which case you will look at the lowest degree or the degree with respect to 1 over Q. So whether you do 0 or infinity, it's really up to you. 0 and infinity have a very special property, which is that they are the only complex numbers whose nth roots are themselves. With 0 you believe it, and with infinity, well, if the inverse of the complex number has this property for its nth roots, so does the complex number. So in particular, if you follow this logic, you can never have roots of unity appearing, because an nth root of unity of 0 is 0 itself. So this generates the famous field of one element that Alan Kohn talked a lot about. Okay, so it really is about the Q equals 0 expansion. So it's a kind of different limit.
This is the famous field of infinitely many elements?
Infinity, I think.
You said Q is infinity, so it's the field of infinitely many elements.
No, I think it's just F1. It really is a field of one element.
But Q is supposed to be the same Q.
Yeah. Okay, so what do we know? We actually know a few things about it. So first of all, we know that this sequence of polynomials always satisfy a linear Q difference equation. So something of this sort. J k plus j of Q equals 0. J goes from 0, say, to d, where a, j of u and v are Laurent polynomials in u and v. Maybe you can take them polynomials. So this is one fact that Tang and I showed some time ago. Of course, every sequence of polynomials satisfies a linear Q difference equation. Just set the coefficients to be 0, but that's called cheating. Yeah?
Why this Q difference equation?
Well, first of all, it has a shift, so you're shifting your discrete variable.
But you in Q difference equation, you shifting the power of Q.
It's because you think of Q difference equations in some bizarre way that you replace x by qx. I mean, it's a different representation of the Q-Weil algebra. It really is a linear Q difference equation here.
No, you just call Q to the n by x.
Yeah, I call Q to the n by x hat, and the shift I call it by y hat, and then y hat x hat satisfy Q to the x hat y hat. If I write it in terms of operator, this linear difference equation is an operator, a polynomial in x hat and y hat. Okay, so that's one thing that that we have. So now here is the next sort of result.
It's only one fact.
That's one fact. Now I need to tell you something more. So here is another sort of theorem. This is myself, which says that if Fn is something called Q holonomic, that means satisfies a linear Q difference equation with no cheating. Okay, then, well, the degree of Fn with respect to Q, now it's a sequence of integer numbers. That sequence of integer numbers is a quadratic quasi polynomial for n sufficiently large. So that's a theorem. That sounds like high school mathematics, and I want to give you some examples. So the first example is, okay, I can take the sequence fn of q, which is minus 1 to the n, q to the n square, and q to the n square, and q to the n. You can convince yourself that this satisfies a q difference, this one does, this one does. The sum of three sequences that satisfy a q difference equation satisfies a q difference equation. Just like the sum of two algebraic numbers is an algebraic number. But if you compute the degree, what do you find? The degree wants to be, this is what it wants to be. It wants to be n squared, and it is n squared when n is even. But sometimes life fails, and it is only n. Okay, but I can always write this in the following way. I can write it as a2 of n, n squared, and a1 of n, and a0 of n, where a I are functions from natural numbers to rationals which are periodic. So a polynomial, a quadratic polynomial of n is, well, what everybody knows. A quadratic quasi-polynomial is a quadratic polynomial whose coefficients are not constants, but they are periodic functions of n. Okay, so, and that's a thing that happens typically happens when you do lattice point counting on convex polytopes. Well, and if you dilate by n, you get quasi-polynomials. So, okay, and unfortunately in our world, q to the n cubed will never appear. This is not q holonomic. So this never appears, so all of our polynomials are quadratic. So this was one example.
And is the constant term, I mean, in your example, which is not a Jones polynomial, the constant term also is periodic, but for the Jones polynomial, isn't it always constant? The leading term.
The leading term in all the examples I know is constant.
Oh, that's not a theorem?
No.
Ah.
No, not yet. No. I don't know. Okay, now let me give you perhaps a different example. So let's look at a version of Fibonacci. So let's look at a kind of Fibonacci-like sequence of natural numbers like an plus 3 minus an plus 2 plus a plus 3an plus 1 minus 13an is equal to 0 with three initial conditions. Okay? So what is this? This is a sequence that satisfies a constant coefficient linear recursion relation. Those, if you go to a good high school, you learn that there is a formula for. You look at the characteristic polynomial, you find the roots of the characteristic polynomial, and then you take nth powers, and if you're unlucky, then you have to take nth powers times polynomials in n. You know, there's the well-known formula starting from Fibonacci type sequences. So yeah, that's kind of easy. So it's a simple thing to show that in this case an times q to the n squared, let's say plus whatever 1, is q holonomic. Okay. Actually, I did say already that sums and products of q holonomic are q holonomic. This sequence is q holonomic. Why? Because it satisfies a linear difference equation where the coefficients are constant. If they are constant, they are allowed to be constant, right? You can't say that q holonomic sequence, this is not q holonomic. Yeah, so it's q holonomic, so this one is q holonomic, and if we calculate the degree, what is the degree? The degree, of course, again, wants to be Well, it wants to be n squared if, but sometimes it fails and it's just 0 actually from here, right? And when does it fail? Well, it fails exactly if the leading term is 0. So these Fibonacci type sequences, of course, the Fibonacci sequence itself has no zeros because it's a sequence of natural numbers. But if I took one of these with some initial conditions and I ask you, what is the structure of natural numbers for which such a sequence is 0? Now, just because we have a formula, the one that involves a sum of nth powers of algebraic numbers multiplied by polynomials of n, just because we have a formula like that, which is a terminating asymptotic expansion, just a finite formula, it doesn't mean that it's so easy to answer the question about what is the structure of zeros of these sequences. And in fact, it is a theorem in number theory of Mahler-Skolem that this set is basically a finite union of full arithmetic progressions up to a finite set, say, of 1 million exceptions. Okay, that's Le Mahler-Skolem. So, why did we get into this? Well, we got into this because if you're going to prove a theorem that says everything is a quadratic quasi-polynomial, you'd better keep this example in mind. So you can't prove this theorem until you have proven or used Le Mahler-Skolem. And the proof of the Le Mahler-Skolem theorem itself, although it sounds elementary, the only proofs I know, but I'm not really an expert, interpolate from natural numbers n, which is the color parameter, not to complex numbers as string theories do in the generalized volume conjecture, but to p-adic numbers. So the proof is p-adic, kind of analytic number theory. The zeros of p-adic functions are much well understood. I should stop here because there are actually some real experts on number theory, and I'm not one of those. So, okay.
So, is this a million like your 3 curves an example, or is this the theorem say that it's universal bound on the size of the exceptional set? You've written what
if I'm given a recursion or
no?
not?
You've written a general theorem for all recursions.
Yeah.
Is it always a bounded number of exceptions or just finite? You've written a million. Was that just to remind us what finite means?
Yeah, just finite. Yeah.
Well, does mean that there's universal?
Undetermined finite. No, it's not universal.
It's not universal. So you better cross out maybe a million.
Yeah.
Right, because a million is actually bounded.
That's right. A million is bounded.
So that's not the theorem. It's bounded.
That's right. So, actually, I'm going to keep this. And actually, there are very interesting problems on basically approximation and S units, as I know, to find, if I give you a recursion like that, in order to find the bounds for these exceptional sets. I learned all these things from van der Putten, whose name I'm probably butchering. Okay, so, all right, so now I can talk about, so with this theorem we can talk about the slopes of a sequence of polynomials which is Q-holonomic. The slopes is just the leading term, the values of the quadratic coefficient here. And by definition, it's always a finite subset of the rational numbers. So the conjecture says that, okay, so these Jones slopes of K are just the slopes of the nth color Jones polynomial. which we decided satisfies a linear recursion. So that's a finite subset of rational numbers, you multiply by 4, and it's always inside BS. But as I said, in all the examples I know, this is just a one-element set. In all the examples I know. So since I gave you the answer for -237, the Jones slope of -237 is, I guess, one of those. And which one is it? So I need to tell you now the degree. So the degree of the Color-Jones polynomial of -237 is exactly equal to, for all n, not just large or whatever, it is equal to 37/8 n squared and 17/2 n, and we can always write this as 37/8 n squared and 17/2 n plus epsilon of n, where epsilon is 0.18, 1/2, 0.18, 1/2, if n is congruent to 0, 1, 2, and 3 mod 4. So you see there is some kind of periodicity. Okay, so for about 3 years, and actually right before I had met Don, I knew this value for the degree of the Color-Jones polynomial, and I was very much, I mean, this number 37/8 kind of mystified me. So I went and I talked to, you know, several topologists. First I thought it has to do with Hovanov homology. It has to do with torsion of Hovanov homology, because -237 is not alternating. Therefore, Hovanov homology is interesting, and it's really interesting in its torsion. So I thought, maybe it has to do with 2 torsion and stuff like that. And the 8, yeah, maybe the 8 may have to do with 2 torsion. So I talked to Peter Oshvat, you know, he said, I don't know, you know, he gave me all kinds of tables, but none of them really match. I talked to Hovanov, you know, he said, not really, you know. Then I talked to Cameron Gordon, you know, and Cameron Gordon told me a very nice story, actually. And the story that he said is that, look, -237 actually is a knot that appears a lot in something called exceptional Dane surgery. So what is an exceptional Dane surgery? Well, first of all, what is Dane surgery? Dane surgery is a way of producing closed 3 manifolds by filling in solid tori in 3 manifolds with torus boundaries. So if we started with a complement of -237 and we do 37/2 surgery on -237, we get the following manifold. First of all, you take a right trefoil and its complement. And then you look at a left trefoil and its complement. And now these are 2 3 manifolds with torus boundary. And you identify them using something like, I'm going to get this wrong, so there's a 6 here and there's another 6 here and something, you know, to fill them in. Okay, and that's what Cameron said, you know, and I said, wow, you know, but why is this an exceptional Dane surgery? It is exceptional in the following sense. -237 is hyperbolic, has a hyperbolic metric. And if you do fillings on a hyperbolic manifold with cusps, in general what you expect is to get a hyperbolic manifold. In fact, the theorem of Thurston says for all but finitely many fillings, which are parameterized by rational numbers, you will get something which is hyperbolic. But this is an example where it's not hyperbolic. And why is this thing not hyperbolic? Because it has a non-trivial so-called JSJ decomposition, which means that this torus here, this torus is an incompressible torus. And hyperbolic closed manifolds do not have incompressible tori. So if you cut the manifold here into 2 pieces along that torus, you get 2 pieces, none of which is hyperbolic. This is kind of doubly exceptional. So, you know, and I said, but how can that happen? So Cameron told me, actually the mechanism of exceptional dense surgery, and all the theorems of exceptional dense surgery boil down to find many examples after a lot of hard work, and this is the key example. So what happens is that you have a genus 2 surface. So the question is, where is this torus coming from? Well, so minus 237 has a genus 2 embedded, incompressible surface. And when you do filling, then what you're doing is you're just cupping, you add 2 little disks, and then you make a closed surface in the 3 manifold. But what happened is that although the original surface was incompressible, when you do the filling and you cap it off, it may be that, that this curve now in the field manifold bounds a disk. And if it does, you cut the disk and the surface compresses to a torus. And if that is a torus, the 3 manifold is no longer hyperbolic. That is the geometric reason of. But these are rare phenomena, and that's exactly what happens here. So I said, okay. He also told me that there is exceptional length space surgery with the numbers 16 and 20, and a few other things. So I said, okay, fine. So then the question is, if this 37/2 on minus 237 has something to do with the 37/8, then there is exceptional dense surgery involved, and that would be great because it would mean that the Jones polynomial knows about non-hyperbolic fillings of a hyperbolic knot. That would be super, because those fillings are not seen by gauge theory. Gauge theory does an average of fillings, but it cannot select. Only BPS can. Okay, so, but then there are disappointing news. There is also another theorem that says that, that a hyperbolic knot has maybe at most 6 exceptional fillings, because pi is 3.14. And also generically a hyperbolic knot has no fillings at all, no hyperbolic fillings, not fillings in the sense of fillings. Okay, so I thought, okay, whatever, but then I went home and I thought a little bit more, and I said, you know what, let's just forget the word exceptional here, and keep in mind, just be positive, and if you're positive, there is indeed an incompressible surface here. Some bad happened to it, but there is a surface here. And then I actually asked Nathan Dunfield next, and I said, what are the set of boundary slopes of incompressible surfaces, and I said, oh, this is the least. And then I thought, this must be the case. So, based on this example and this example alone, I formulated the slope conjecture. And afterwards I went to see Don, and Don said, I want a formula for the recursion of the Color-Jones polynomial minus 237 pretzel. So, which was years worth of work.
As I mentioned, yeah.
Yeah. So okay. So that was really kind of the slope conjecture. So, but things were a little too easy, I must say, because in fact, dangerously easy. Because now, okay, if you have a conjecture like that, then you need some examples, and there is one class of knots which is easy from that point of view, and that class of knots is the alternating knot. So alternating knot, what does it mean? It means you do this, right? Probably Kaufman will do things like that, and then you just make it alternating, right? In one of 2 possible ways. So here's an example of an alternating knot. And for alternating knots, we know, not because of state-sum formulas for the Color-Jones polynomial, but because of something called the famous Kaufman X. Huh? Should I keep going?
2Fs.
But it's 2 F's and 1 N. Yes. I always think it's not the German spelling. Thank you. So because of that, it's actually, which basically says that you can resolve the crossings this way. It is possible, with coefficients, of course, but I'm going to get it. Road conventions, which is possible, out of all these cube of resolutions, it is possible to actually figure out, for alternating nodes, the unique resolution that gives you the highest term. And if you do that, you're going to find out that this coefficient here, this leading coefficient here, in fact, is a number, and the number that it is the number of positive crossings divided by 2. So the degree of the Color-Jones is this n squared plus, the other terms, which I ignore, where C plus is the number of positive crossings. So if you multiply by 2, then you get 2C plus. So you get the JS of an alternating knot here is exactly twice times the number of crossings. That's a very interesting thing because, alternating knots, if you're really talking to a topologist, alternating knots have no reason to exist, knots exist, but alternating knots, what is an alternating knot? Give me an intrinsic definition of an alternating knot, in particular of the number of positive crossings, and the fact that the number of positive crossings is seen in the Jones polynomial means that it is an invariant of alternating knots.
Isn't the number of negative crossings the same since it alternates?
No. If you take the mirror image, you're going to get minus 2C minus.
Wait, no. So C plus and C minus are not the same?
No.
I thought alternate means it alternates between.
Yeah, it alternates, but if you flip all the crossings, all positive become negative and vice versa.
If you go around the thing and it alternates.
Oh,
plus minus.
I think we should do an example of 5-2.
You're not worrying about this for the highest degree.
Yeah, I think we should do 5-2.
No, but I'm just asking.
No, just because a crossing alternates, it doesn't mean that if one is positive, the other is negative. It alternates in the sense that if you go above the bridge here, you're going to go below the bridge there.
Isn't that what positive?
Oh no!
There's an orientation, I see.
Yes, positive and negative.
Okay. Thank you, that explains my confusion.
Okay, so alright, so actually 5-2 has...
no, I believe you that if the argument is wrong...
5 positive and... yeah, okay. So then I went actually back to Cameron, very scared. So I knew of a paper of Bill Menasco, talks about, alternating knots are hyperbolic, and there's a series of papers. Unless they're connected sums or torus knots or something. So anyway, in the series of papers, Bill Menasco, has a paper that studies incompressible surfaces on alternating knot complements. In particular, 2 of those surfaces are very interesting. If you have a planar projection, you can do the checkerboard coloring, which here takes a lot of time to checkerboard color. And these 2 surfaces, although not in general oriented, if you take the double of them, you can make them oriented. So those 2, Menasco proved they're incompressible. So here, if you look at the biggest degree is 2C plus, if you look at the lowest degree is minus 2C minus. So I have 2 specific numbers here. I wanted to find surfaces with these boundary slopes. And all I knew was that the checkerboard surfaces, which are always 2, there is a black and a white, are incompressible.
But not orientable.
But not orientable, but you can double them to make them orientable.
4, since 4 is not 1, it's 4J sub K is this.
Yes, thank you. 4, yes. So I went back to Cameron and I said, okay, do you know what are the boundary slopes of the checkerboard surfaces? And Cameron said, oh, it's just trivial, it's like number of positive crossings or negative crossings. I said, how do you prove that? Because it wasn't in Bill Menasco's paper. He said, oh, well, he showed me. He showed. So then, it means that actually BS of an alternating knot always includes 2C plus and minus 2C minus, and it includes other stuff. So at that point, I knew at least that slope conjecture was true for alternating knots. Okay, and then you can do the case of torus knots, but for the torus knots you can use you can use a formula by Rosso and Jones, which is also used in matrix models somehow. to study torus knots. Then that formula also has a single term. I mean, it's a sum, but out of the sum, only one term really contributes. And you can prove the slope conjecture for torus knots, or check the slope conjecture for torus knots. So I was like, okay, I mean, and then just to be on the safe side, I went to the table of knots with 8 and 9 crossings. There's only 3 with 8 crossings which are not alternating. There's about whatever 15 or something like that of 9 crossings on alternating, and I checked for every one of them that being Montesinos, I could compute the set of boundary slopes here, and I could compute the degree or guess the degree, and somehow it fits. So okay, I guess that was the conjecture. All right. Now, where does this thing fit? You know, I told you a little bit about the field of one element, I mean, which is whatever that thing means. I told you that it has to do with the Q equals 0 expansion. It also has to do with the so-called tropical limit. So, because the degree of the product of two polynomials is always equal to the sum of the degrees, and the degree of the sum is optimistically equal to the maximum of the degrees, except when there is cancellation, and that's just not true. But if you use these as axioms, then you can define a semi-field, I mean the tropical limit. Okay, so I guess, I mean, if you really thought that Q was some kind of Keller parameter, we're talking about the large radius limit. There's where all the geometry degenerates to maybe some toric geometry, and that's all you're seeing out of the Keller class. So that's kind of, you know, where this thing fits. But I want to, oh, okay, that means I have to, do I have 2 minutes or something?
Yeah, 2 minutes.
Okay, okay, I do want to say a couple of things. So the volume conjecture was already mentioned. So Rinat's volume conjecture was mentioned, and known for basically only the figure 8 knot as far as hyperbolic knots goes. Then there was this AJ conjecture that was also mentioned, that has to do with the relation of the minimal order Q difference equation for the Color-Jones when you put it Q equal to 1. Okay, and that is an easier conjecture because this is algebra. Well, not Q commutative algebra, but it's still algebra. This one is hard. It's complex analysis. You have to talk about asymptotics of multidimensional integrals, which are not governed by Hodge theory or Picard-Fuchs equations, because the quantum dilogarithm does not happen to satisfy one of these equations of algebraic geometry. So that's a very hard conjecture. I even heard a joke once that Rinat was in front of a committee and they said, oh, but you formulated your volume conjecture, but you haven't proven it. What is going on after all these years? So I think it's a wonderful conjecture because, okay, and then there is this slope conjecture, which is basically the Q equals 0 limit. Now I do want to say one thing. So here is a little sort of lemma. So if the AJ conjecture holds, and the Newton polygon of A hat is equal to the Newton polygon of A, then slope conjecture holds. And the reason for this is because once you know the regularity for the degree, and you know there's a Q difference equation, if you put the two together and you look at highest degrees, you will see that the slopes are slopes of the Newton polygon of A cut. And if these two are equal, they're slopes of Newton polygon of A. And Kuller and Schalem theory tells you that the slopes of Newton polygon of A are boundary slopes by some action on trees and so on. So, in a sense, this is an easier conjecture. There is also joint work with Roland that proves it, reduces it to some quadratic integer optimization problem, a tropical one that often is solvable. So you can actually generate kind of automatic proofs of the slope conjecture for vast classes of knots, but so far not for general sort of knots. So this is an easy case compared to that and compared to that. That's all. Yeah.
Well, the sort of obvious one, the question I asked before, and you confirmed that in all known cases, and maybe conjecturally, always JS of k is a single number. So do you have any conjecture how to pick out which incompressible surface it's supposed to be?
Yeah, and if I had given you the table of 0, 16, and 37 over 2 and 20, why would you choose the one there?
Well, it's the
right. So
that's the highest order.
But do you have any?
So this is similar to the problem of, so the color Jaws is annihilated by, maybe you can make it homogeneous linear recursion, which means that the color Jones has cousins, namely the other solutions of that recursion. So altogether, there is a vector space worth of invariants that may be related to things like the index of Dimov, Gugov, and Gaiotto, or may have to do with conformal blocks. So physics tells us that maybe we shouldn't be talking about one sequence or one vector, but a finite vector space that is a solution to a single equation, like a Gauss-Manin, but like in the Q world. So and then the cousins would pick up
the others,
remaining slopes, but only the so-called visible slopes, because there are some dark slopes that have to do with holes on the character variety. I mean, I can tell you more.
Or is this about slopes of the Newton polygon and its convex hull?
That's right, that's right. So you're supposed to pick at least all of those up.
So you're saying instead of making VS smaller and picking out one, you make JS bigger and pick out everything?
Yes, yes. And bigger and more invariant. But up to now, that story that the Color-Jones polynomial, which is a sequence of polynomials, is really some vector in a finite dimensional space. Even the dimension of that space is, the order of the recursion. It's an interesting, not invariant, but a hard one. So, a Q version of a D module, right? A Q holonomic D module. That does not exist mathematically. So I cannot talk about the sisters of the Color-Jones yet. Yeah, but I suspect that if you formulate correctly, but that doesn't answer your question, because your question is, even if there is a vector space, there is a selected
vector on the left,
vector
on the right.
So and nobody.
Well, here you said it's the black checkerboard.
Yeah,
that was the right incompressible surface.
That's right.
So here.
Yeah, except if you follow this, somehow if you do drawings of surfaces, then you tend to get only surfaces of integer or half integer slopes. And we had a famous knot 1079 with Nathan Dunfield, and we produced through some other criterion a slope 10/3. And there was a conjecture up until a few years ago that alternating nodes have only integer boundary slopes.
No, but this isn't the Jones slope. This is some other one.
Yeah,
But I'm asking only about the Jones
Right,
one, which
right.
is half integral. You just told us that.
Yes. So there is more. You know, in fact, I do have quite. I mean, people who do topological recursion, they tell us that you have to choose very carefully initial conditions, so that the asymptotics of J hat of Color Jones is matching that. So, but what happens to the cousins? I mean, are they different initial conditions? I mean, because you have to. I don't know. I don't know how Jones selected that vector.
More questions? Let's thank the speaker again.